Yes. So my name is Pujith Vijayaratnam, and as Penny mentioned, my topic is alleviating the adverse hemodynamics of arteries treated with drug-eluting stents. Now, as some of you may already be aware, currently the biggest killer of Australians at the moment is heart disease. So in 2013 alone, almost 20,000 Australians passed away as a result of heart disease. So among women, it caused 3 times the number of deaths as breast cancer. And among men, it caused twice the number of deaths as lung cancer. So it is by a considerable margin the biggest cause of mortality in Australia at the moment. And it is primarily caused by a disease by the name of atherosclerosis, which is basically the buildup of plaque within the arteries, as may be seen in this image over here. So this plaque buildup over here, that doesn't necessarily have to occur within the arteries supplying blood to the heart. It can also occur within the carotid arteries, which supply blood to the brain, and this is actually the primary cause of strokes. Furthermore, it can also affect the blood flow to the arms, the legs, the pelvis, and also the renal arteries, which supply blood to the kidneys. So there are a few methods of treating this disease at the moment, and currently the most common is called balloon angioplasty. Hopefully you can all see that balloon over there. So basically, this procedure works by feeding a very small balloon catheter to the site of the arterial occlusion. And by expanding this balloon, it basically compresses the plaque up against the artery wall, thereby restoring blood flow to the vessel. Now, if you used a balloon on its own, the problem that you might find is that the artery has a tendency to collapse on itself due to the elastic nature of the artery tissue. So to circumvent this problem, most of these balloon angioplasty procedures are coupled with the implantation of stents, which are these metallic wire mesh devices that you can see up here. Now, I mentioned earlier that my topic was alleviating the adverse hemodynamics associated with stents. And what I mean by that is that although the stents do serve to improve the overall blood flow to the vessel, what we do find is that in the regions before and after each of the stent struts, we get localized regions of recirculating flow, as may be seen here and here. Now, the problem with these recirculating flow regions is that they correspond with regions of low wall shear stress, which is the tangential stress imparted on the wall due to the viscous drag of the blood. And furthermore, we also get localized regions of relatively high wall shear stress along the top of the stent struts as well. Now, the reason why these non-physiological wall shear stresses are bad is that the cells which comprise the inner layers of the tissue are actually very sensitive to changes in the wall shear stress environment. So what I mean by that is that these endothelial cells, which line the inner walls of the arteries, they are actually removed in regions of low wall shear stress, so in these regions here. And what this does is that because the endothelial cells actually act as a barrier for smooth muscle cell proliferation, once these endothelial cells are removed, the smooth muscle cells underneath have a tendency to migrate into the main vessel and subsequently re-occlude the vessel. So this here, these white spaces, are where the stent was originally implanted, and all of this extra mass is just due to smooth muscle cell proliferation. Now, this disease, which is known as neointimal hyperplasia, it was found in approximately 20 to 40% of cases involving the original stents, which were called bare metal stents. But what I'm focusing on is called a drug-eluting stent. And what these devices do is that they have a drug coating, which may be seen by the black regions over here. And the drug in this coating serves as an anti-proliferative agent, basically, so it prevents the smooth muscle cells from proliferating too much. And basically, this reduced the tendency of this happening from 20 to 40% to about 5%. However, there is another disease which we have to worry about with these devices, and that is known as stent thrombosis. And that is basically the formation of a blood clot, which is this big red region over here, within a stented artery. Now, these blood clots are also thought to be related to the shear stress environment. For instance, in this high wall shear stress area, we see that platelets, which are the cells responsible for causing blood clots, they actually become activated, which means that they want to start to sort of clump together, I guess. And These activated platelets can subsequently go into these recirculation zones, as shown here, and accumulate to high concentrations. And this can subsequently allow a blood clot to form, as shown in here. Now, this is a comparatively rare disease, whereas that neointimal hyperplasia was observed in 5% of cases. In this case, it's observed in only about 0.5% of cases, but this has a mortality rate of 45%. So 45% of cases in which these blood clots occur are actually fatal. So you may be wondering at this stage, why is it that these stents are still designed with this non-hemodynamic square strut profile? And the reason for that is that numerical studies have shown that this square profile actually enhances the drug transport into the tissue. So if we look at these recirculation zones here and here, we see that the drug, which is shown in blue, it elutes from these non-contacting surfaces, and it actually forms localized regions of high concentration in these recirculation zones, and this can subsequently enhance the diffusion of the drug from the blood into the tissue. Now, previous numerical studies have shown that this flow-mediated drug transport can actually account for about 90% of the overall drug uptake. So from these results, we can conclude that it's important to ensure that the blood is modeled accurately when we try to simulate the drug transport environment of arteries treated with drug-eluting stents, and hence that was the first aim of my thesis. And the second aim was to experimentally validate these results. Well, finally, I wanted to work out how to alleviate the adverse hemodynamics without compromising the overall drug uptake. So in order to work out how the blood flow affected the drug transport, I performed a series of computational fluid dynamics analyses. Now, this basically involved solving the Navier-Stokes equations within the lumen here, so that resolved what the blood flow was doing. And I also performed a series of scalar advection diffusion equations to model the diffusion of the drug from the stent coating into the lumen and also into the tissue. In my initial analyses, I wanted to see what impact the non-Newtonian nature of blood had on the overall drug uptake. So blood is actually a non-Newtonian fluid, although it's commonly modeled as a Newtonian fluid just for convenience. And what I found was that in each of the blood models that I implemented, a very asymmetric distribution of drug was noticed in the actual tissue, and this showed the impact of the flow-mediated drug transport into the tissue. And furthermore, we noticed a very considerable difference in the overall drug uptake. So these red regions here show where the non-Newtonian model predicted a higher drug concentration than the Newtonian model. So there was a very big difference. However, there's also a very big limitation in this study, and that is that the drug coating on the outside of the strut was actually assumed as being time invariant and also as being constant along each of the surfaces. Now, the reason why that boundary condition is employed in several numerical studies, actually, is because the drug actually elutes from these struts over a period of several weeks, if not several months in some cases. So most people assume that the depletion of drug at the actual coating surfaces is negligible. So I wanted to see if it truly did have an impact to model this depletion of drug. And I also wanted to see the impact of blood's pulsatile flow. So I performed a series of transient simulations in which I modeled the blood flow as being pulsatile and compared that with steady flow simulations. And I also compared the Newtonian and non-Newtonian models in this case as well. Now, these are much more computationally intensive than the previous cases. Similar to Kyle, my cases took about 2 months to actually run, and this was just for 60 seconds of data. But at the outcome of the at the end of the 60 seconds, what we noticed was that unlike the previous studies, there was actually no difference, or less than 0.5% of a difference, between the Newtonian and non-Newtonian, between the overall drug uptake between the two models, which is completely against what we found earlier. So in order to work out why this happened, I had a look at the drug concentrations along the outside of each of the stent along the outside of each of the stent surfaces. And what I found was that the drug concentrations along this bottom stent surface which is the surface that's in contact with the tissue, was actually an order of magnitude higher than anywhere else along the strut. So what this implies is that the drug is actually being depleted from these three non-contacting surfaces at a much quicker rate than it is from that bottom surface. So because we didn't see any difference between the models at this 60-second mark, we assumed at this point that the flow-mediated drug transport is actually negligible. So in order to confirm this, we performed two further simulations. So these, unlike the previous ones, were performed over 24 hours using a steady flow model. So the case that you see on the left here, in that case, I assumed that the drug was allowed to deplete on all four surfaces of the strut. So it was allowed to deplete into the lumen, into where the blood flow is, I should say, and also down into the tissue as well. Whereas in the right-hand case, I only allowed the drug to be depleted from the bottom surface. Therefore, the drug could only diffuse from the strut into the tissue, and it could not go into the blood flow. So the results of this analysis showed an identical drug distribution in the tissue. So this confirmed that the flow-mediated drug transport is effectively zero, contrary to what was found in previous numerical studies, which showed 90% of it is flow-mediated. Now, none of these results would really mean anything unless we experimentally validated them. And to do this, I employed the experimental model developed by my predecessor, whose name is Caroline O'Brien. So she developed this experimental rig, and it basically serves to analogously represent what I showed in the computational studies. So as in the previous studies, a strut is used to simulate a drug-eluting stent strut, except in this case, it features a fluorescent dye. So it's basically a silicon strut infused with a fluorescent dye, and it sits on top of a hydrogel, which is used to simulate the artery tissue. And over the course of 3 hours, a blood analog fluid is allowed to be pumped using a peristaltic pump through this flow channel and over the top of the hydrogel and the strut. So in the end, the distribution of the fluorescent marker that is being eluted from the strut into the hydrogel is used to analogously represent the diffusion of the drug from the drug-eluting stent into the artery tissue. So these are the results that I got. And as you can see, the distribution of the marker in the hydrogel, once the hydrogel had been cross-sectioned, is very, very symmetrical, which is completely different to what we found in our very first study, which assumed a constant concentration of drug along the strut surfaces. So this seems to imply that the second model that we employed is the more appropriate model to use. And so we performed another computational simulation using this updated model, and we found a very similar drug distribution, although the overall magnitudes of the drug are quite significantly different at this stage, and that's because I used the diffusion coefficients provided to me by my predecessor, and I'm still working on trying to get my own diffusion coefficients because I used a slightly different concentration of drug in my strut. But nonetheless, we have achieved qualitative validation of our computational model at this stage, and from this we can prove that the flow-mediated drug transport is actually zero, basically. So having established this, in seeking to find out how to alleviate the adverse shear stresses without compromising the drug transport, this actually made things a lot simpler because all we had to do was extend the region of contact between the strut and the tissue, or between the drug coating and the tissue, rather. And because we could get rid of these three regions of the coating, we could actually reduce the height of the strut as well, and also make the strut a more hemodynamic profile. So I should mention as well that both of these struts feature the same amount of material. So the white regions that you see here and here are actually the same area, and the thickness of the coating is identical in both models as well. So the results obtained from our initial 2D analyses showed that by extending the contact region between the strut and tissue, we actually get a 65% increase in the overall drug uptake in the tissue. And furthermore, we also see a dramatic reduction in the size of these recirculation zones, as we would expect. But in cases in which the strut is not contacting the tissue, we also saw an even greater reduction in the size of these flow disturbances. So in our final simulations, we performed a couple of studies with using more realistic geometries. So in these three-dimensional geometries, we observed a 58% reduction in these blue regions here, which are the regions exposed to low wall shear stress. And we also saw a 74% reduction in the areas exposed to high wall shear stresses. So from these, we hope to see that because the recirculation zones are reduced, we hope to see that a complete endothelial layer will in the future be formed once these struts are refined a bit further. And as a result, we hope to see that the onset of those diseases that I outlined earlier will be reduced as well. Now, there are some limitations in this study, obviously. Like, I haven't looked at the impact of changing the strut profile on the mechanical integrity of the stents themselves. And I also haven't looked at the impact of changing the strut profile on their ability to be expanded by the balloon. However, it does at the very least provide a direction in which to design the struts to, first of all, alleviate the adverse hemodynamics, and secondly, to enhance the drug transport into the tissue. So in conclusion, the flow-mediated drug transport has been proven to be effectively zero in both computationally and experimentally. And finally, the drug transport into stented arteries can be enhanced just by using a more streamlined strut profile and increasing the region of contact between the drug coating and the tissue. So thanks for listening to my speech.